Hi, here we have another question from Iran Mathematical Olympiad round number 1, year 1997. The question says, how many sequences of natural numbers n1, n2, n3, and so on satisfy the following equation: nk plus 1 larger than n of nk? First round of Iran Mathematical Olympiad is usually consists of multiple choice questions. You get 30 questions for 3 hours. So each question approximately 6 minutes. This question was a little bit difficult one to my taste. So maybe I spend 10 to 15 minutes try to solve this exercise and then come back and see the solution. The options that we have, first one is there exists infinitely many sequences with this property. There exists an even number of such sequences. We have exactly 5 sequence, we have exactly 3 sequence, and we have exactly 1 sequence with this property. All right, let us look at the solution. This is the property that is given. Let us assume nk is the minimum value in this sequence. So we have this sequence, one of them will be the minimum. We take it as nk. So we know that based on this property, nk is larger than n of nk minus 1. But this is already a contradiction because we said nk should be the minimum number. And now we say that nk is larger than this number. That means we should not have this number in the sequence. When we don't have this number in the sequence, if k is equal to 1, because then we will have n0, and obviously we don't have n0 in this sequence. Therefore, this is a contradiction, and that means k has to be equal to 1. So n1 is the minimum of the sequence and is lesser than ni if I is larger than 1. All right. I want to prove that n1 is less than n2 is less than n3 and so on. So I want to prove that this sequence is a strictly ascending sequence. And we are going to do this with mathematical induction. So for n equal to 1, we know it. So n1 is less than ni for I larger than 1. We assume that n1 is less than n2 till less than np. And for any I larger than p, ni will be larger than np. This is our assumption, and we have to prove that n1 is less than n2 till np is also less than np plus 1. And then less than ni I larger than p plus 1. If we can prove this from these two given information, then basically we have shown that this sequence is an ascending sequence, n1 is less than n2, and so on. All right, so let's see how we can show this. First of all, because this is an ascending order from n1 to np, that means np has to be equal or larger than p, because these are natural numbers, and if they are in ascending order, this means the minimum of np can be equal to p. So we know that np is equal or larger than p. And because this other one, ni, I is larger than p, that means ni will be equal or larger than p plus 1, because I will be equal or larger than p plus 1, therefore ni will be equal or larger than p plus 1. So this is the information that we already know. Again, let's assume that nq is the minimum number among this ni for I larger than p. If q is equal to p plus 1, then we have already completed the proof, because we have shown that this is true and this is less than np plus 1 and less than all the other ni for I larger than p plus 1. And that completes the proof. Now let's assume q is larger than p plus 1. So nq is the minimum among these and q is larger than p plus 1. So now we are going to calculate nq minus 1. Okay, so we know that nq minus 1, because q is larger than p plus 1, q minus 1 will be larger than p. And since here we know that ni, if I is larger than p, all of them are equal or larger than p plus 1, that means nq minus 1, it will be equal or larger than p plus 1. All right. Now, In the main equation that we have, nk plus 1 larger than n of nk, we put k equal to q minus 1. So this first part, the left part, become nq. It will be larger than n of nq minus 1. But we know that q minus 1 itself is equal or larger than p plus 1. Okay, so if this is equal or larger than p plus 1, that means this number belongs to this set, and I larger than p. But we assume nq is the minimum of this set. But now we show that nq is larger than another number in this set, which is a contradiction. Therefore, it means that q cannot be larger than p plus 1. Q has to be equal to p plus 1. And we know that all of these numbers, I is already larger than p. So the only option that we have, q has to be equal to p plus 1. All right, so basically we have completed the mathematical induction, and we've shown that n1 is less than n2 till np less than np plus 1 and less than the rest of the sequence. Basically, we say that the sequence is an ascending sequence. Okay, we know that nk is equal or larger than k because this is an ascending order and these are natural numbers. So nk has to be equal or larger than k. And we know that nk plus 1 is larger than n of nk. That means nk, this index, has to be less than k plus 1. Because if this one is larger than k plus 1, this is a contradiction because we have shown that this sequence is an ascending sequence. If this is larger than this, then n of nk has to be larger than nk plus 1. So we know that nk has to be less than k plus 1, and we know that nk has to be equal or larger than k. That means nk has to be equal to k. Therefore, we have only one sequence, and that is nk is equal to k. So the correct answer will be option E. Let's see what we have learned through this exercise. Consider the minimum or maximum elements of a sequence or a set. Use the given properties and try to identify additional conditions or properties. So taking the minimum or maximum elements of a set usually give you some additional information which you can use to prove the exercise. Use mathematical induction to prove the general term of a sequence. Alright, so that is the end of the video. I hope that you learned something new. See you next time. Bye.